Last week, we explored the dewatering process used in the early foundation phase of the Markthal project in Rotterdam. The Markthal in Rotterdam showcases innovative engineering in response to complex urban soil and groundwater conditions. Initial excavation used a combi wall and over 2,200 foundation piles to stabilize the site with water-filled pits balancing groundwater pressure before underwater concreting. Dewatering was managed through pressure relief systems, deep wells, and real-time monitoring to prevent uplift and protect nearby structures like the Lorenskirk. This week, we focused on the construction of the iconic arch, built in 4 segments with temporary supports and a central keystone. The arch's forces were balanced through tension steel cables and a flexible, transparent cable net facade, engineered to withstand wind-induced deflection while preserving interior openness. The construction of the Markthal in Rotterdam exemplifies a sophisticated use of tunnel formwork to build its unique arch-shaped structure, particularly for the 2 vertical legs on each side of the arch. This construction method was instrumental in maintaining the pace, quality, and integrity of the project, which could otherwise have been slowed down significantly by its architectural complexity. J.P. van Eesteren utilized tunnel formwork for the construction of the 2 vertical legs of the Markthal. This choice was particularly suited for the repetitive nature of the residential units along each side of the arch. Unlike conventional methods where walls and slabs are cast separately, tunnel formwork allowed them to be poured together in a single, continuous operation for the Markthal's residential units from the 2nd to the 10th floor. The construction progressed floor by floor, each composed of 15 cells per side of the arch. Each floor was completed within a day, reflecting the speed and efficiency that tunnel formwork can bring to a project. Steel L-shaped tunnel forms were positioned and aligned meticulously. Steel reinforcement bars were placed to ensure structural continuity throughout the building. Embedded services, such as plumbing, electrical conduits, and ventilation ducts, were incorporated before the concrete pour. Concrete for both walls and slabs was poured simultaneously for a monolithic structure. Once the concrete achieved sufficient curing, the forms were detached for the next cycle. The tunnel form units were hoisted to the next level using cranes every day, enabling a brisk pace of construction at a rate of 1 floor per day. This efficiency was crucial to maintaining the tight project timeline without compromising on quality. Traditionally used for linear and vertical structures, the tunnel formwork was adapted to accommodate the gradual inward curve required to form the arch. With each succeeding floor, the angle of the slabs was incrementally modified. This adaptation allowed the 2 vertical legs to converge and meet at the apex, forming the central arch, while ensuring precision and structural integrity. Tunnel formwork played a crucial role in Markthal's construction, particularly for the efficient assembly of its apartment wings. The method's speed, reduced labor need, and high-quality finishes were ideally suited to the project's repetitive design, highlighting the benefits of this formwork system in large-scale modular architecture. The construction of the Markthal demonstrated not only the efficiency gains from using tunnel formwork, but also its adaptability to complex architectural designs. This approach showcased how a traditionally linear construction technique could be modified to execute Markthal's curved geometry, merging architectural creativity with construction practicality. The arch was completed with the placement of a keystone element at the apex. This piece was crucial in locking each of the 4 sections together, allowing the structure to transfer load effectively from the roof to the vertical legs or walls. Upon the keystone installation, the arch achieved self-support, with loads being efficiently channeled down the curved surfaces to the vertical supports and further into the foundations. The arch's design allows loads to be transferred horizontally along the curve through compression, ultimately directed downwards to the foundation through its legs, without internal columns disrupting the interior space. The arch was constructed from 4 primary segments, each carefully placed to maximize stability and load distribution. For each of the 4 roof sections, temporary supports were critical. 2 substantial temporary support towers were erected under the arch. The support tower provided stability to the 2 sections of each floor during construction and curing phases. Loads on the Markthal's arch originate from the roof and any additional superimposed loads, such as snow or wind pressure, acting downwards. These loads are transferred horizontally along the curve of the arch. The arch's material and geometric design facilitate this, as each segment, voussoir, pushes against its neighbors, efficiently translating vertical loads into compressive horizontal forces along the arch. At the arch's springing points, where the arch meets the vertical supports, the structure experiences horizontal thrust. This is a natural consequence of the curved shape trying to spread out under load. The Markthal's design ensures that the vertical supports, walls or legs, are robust and well anchored. These supports must be capable of resisting the outward thrusts to maintain equilibrium and prevent any lateral displacement. After the arch efficiently redistributes the loads horizontally, these loads are subsequently directed down the vertical supports towards the foundation. This path ensures that the foundation bears the final weight of the structure, allowing forces to dissipate safely into the ground. The foundations must be designed to distribute these final loads broadly enough to prevent uneven settlement and maintain structural stability over time. The placement of the keystone at the arch's apex locks the arch segments into a stable configuration where the flow of forces converts purely into compression. This ensures that the arch does not require additional internal supports or columns. Thanks to this efficient load transfer mechanism, the Markthal can maintain large open interior spaces. This is particularly beneficial for its function as a public market hall, providing a vast, unobstructed area. The design of the Markthal's arch showcases engineering principles of how forces are managed in an arch structure. From initial load application on the roof to final distribution into the foundations, the arch's curvature enables efficient load movement through compression. This system ensures not only the structural integrity of the Markthal, but also contributes to its iconic architectural presence with an expansive, open interior. At the base of the arch, where the legs meet the foundation, horizontal thrust is naturally generated as the arch spreads outward under load. To resist this, engineers installed tension anchors and integrated tensioning systems beneath the structure. These systems stabilize the arch and help complete the structural force loop. But structural support didn't stop there. At both ends of the Markthal, the cable net glass facades also act in tension, reinforcing horizontal stability. They form a key part of the structure, not just a cladding, but a structural element. Each facade spans an impressive 34 meters in height and 42 meters in width. They represent a bold fusion of architectural transparency and structural innovation. The facades are made of 22 horizontal and 26 vertical galvanized steel cables, forming a precise grid of 1.5 by 1.5 meter sections that hold the glass panels. This grid ensures both strength and visual openness. Each cable, 31 millimeters in diameter, is pre-stressed between the concrete arch and the foundation, anchored into heavy steel boxes embedded within the structure. This tensioning creates a secure enclosure without relying on conventional bulky frames or mullions. Using a hydraulic tension bridge, the cables were tensioned gradually up to 300 kilonewtons, stretching each by approximately 150 millimeters. An additional 50 kilonewtons of reserve capacity was built in to absorb long-term creep in the concrete. This high-tension system keeps the facade taut and stable, allowing for its large, frameless appearance while still handling substantial structural loads. However, this flexibility introduced new challenges. The facades are subject to significant wind-induced deflection, up to 700 millimeters inward or outward, totaling 1,400 millimeters of movement at the center. To manage this, the glass is attached with joints that allow controlled flexibility. Silicone joints between panels absorb movement while maintaining weatherproofing and airtightness. At the corners, rubber profiling protects the glass from excessive torsion. In frameless zones, butt joint sealants fill the gaps, ensuring a smooth and continuous surface. These details allow the glass to flex and shift as needed, without compromising its structural integrity. Thanks to this system, the Markthal facades not only support the building, but also welcome light, frame open views, and define a truly transparent public space. This week, we focused on the construction of the iconic arch. Built in 4 segments with temporary supports and completed with a central keystone, the arch used high-tension steel cables and a flexible cable-net glass facade to manage structural forces, allowing for a spacious, column-free interior while maintaining stability under wind loads. Next week, we'll explore how the Markthal integrates ventilation systems and underground heat storage to enhance energy performance and indoor comfort.